My name is Nick Moskowitz. I'm a planetary astronomer here at Lowell Observatory, and my research interests are in small bodies in the solar system, so meteors, asteroids, and comets. Asteroid Day marks the anniversary of the Tunguska impact that happened back in 1908. The Tunguska impact was a relatively large body, maybe 50 meters in size or so, that came in and impacted and actually exploded in the atmosphere above Siberia in Russia. And it leveled hundreds of square miles of trees and caused fairly large-scale destruction. And it was one of the largest impacts on Earth from a body from outer space over the past few centuries. And so every year on the anniversary of Tunguska, we celebrate Asteroid Day to recognize and raise awareness about asteroid science and what efforts are ongoing to hopefully prevent future impacts like Tunguska.
All right, my name is Matthew Kent. I'm the president and CEO of Meteor Crater Enterprises. Welcome to Meteor Crater. I've been here for 3 years, serving in this capacity, and it's a very exciting time for us here, so welcome. Asteroid Day is a very important day. It's a United Nations recognized day. The day originated in 2016 by an organization called the B612 Foundation. And B612 is a collection of astronauts and scientists from all around the world. And their mission is to bring awareness to asteroids and the potential impact of meteorites and catastrophic impacts on Earth. Meteor Crater is a great example of what happens when a meteorite hits Earth on a large scale. But it's not a matter of if it's going to happen, it's a matter of when it's going to happen. And B612 is dedicated to doing the science, the research, and coming up with a strategy to protect Earth. So as you can see, very important. Meteor Crater is the best preserved impact site on Earth. It's not too different than when a meteorite came out of the east and hit Earth 50,000 years ago. It hit with the force 150 times greater than an atomic bomb. It destroyed every living organism and life form in a 7-mile radius. Space is now bigger than ever. And every person in America and around the world is fascinated with what's out there in the history of space travel. And Flagstaff, Arizona and Northern Arizona, you have Lowell Observatory and Meteor Crater, 2 premier destinations and attractions for astrotourism. And between the astronomy and the research conducted at Lowell and the physical presence of what happens in the world of meteorites here at Meteor Crater, it tells an amazing story about the beginning and the end of impact science. We just look forward to bringing all of this education and science to everyone.
My name is Danielle Adams, and I'm the Chief Marketing and Revenue Officer at Lowell Observatory, and I am a cultural astronomer. Asteroid Day is an opportunity to think about the near-Earth objects that are out in space that could potentially threaten the Earth one day, and the need to discover these objects and plot their trajectories and orbits so that we can help keep Earth safe and know if any of these objects are going to come near the Earth. Here at Meteor Crater, this is also a great opportunity to see what happens when one of those asteroids does actually come and impact the Earth. So over our 128-year history so far, Lowell Observatory has discovered more than 30,000 asteroids. And this is a critical beginning to the process of identifying those things that are out in space and plotting their trajectories, determining their characteristics, so we know which of these objects might at some point in the future impact the Earth, or at least come close to doing so. So that's the beginning of the story. And then here at Meteor Crater, we have the end of the story. What happens when one of those objects actually does come and impact the Earth? When we talk about trying to defend the Earth from asteroids, a lot of people think of Armageddon and Deep Impact and other Hollywood movies. And, there is real science that's being done to first try to find the asteroids and identify their orbits, but then also to figure out, what kind of options might actually work to slightly deflect the asteroid in its path so that it misses us instead of hitting us. And the DART mission is a fantastic example of that, where we're going to have a spacecraft actually impact one of a pair of asteroids that orbits around each other, and see what the change is in real time and over a period of time after that in the orbits of these asteroids. So that's real science as opposed to what we might see in Hollywood.
So Lowell Observatory has a long history of research in asteroids and near-Earth objects. We use telescopes and computer simulations and models to try to understand the population of asteroids in the solar system. How many are they? What are they like? What are the nature of these bodies? What are their surface properties? What are their interior properties? Where did they come from? And at least from the impact hazard perspective, what is the likelihood of any of these going to hit the Earth anytime soon? So the NASA DART mission is a mission that is the world's first real planetary defense mitigation experiment. DART is an acronym that stands for the Double Asteroid Redirection Test. And so the spacecraft will be hitting a double asteroid. It's a binary asteroid where Didymos is the larger body and Dimorphos is its small satellite. And the DART spacecraft will be hitting the Dimorphos satellite. The spacecraft will impact at over 10,000 miles per hour onto this asteroid and look at how much the asteroid will be deflected in its orbit. And that will be an important test if we ever had to do this for real. If we ever found an asteroid that was on an impacting trajectory and had to deflect it so it would not hit the Earth, we want to make sure we know how to do that. And DART is the first ever test of that process. And so it will be impacting on September 26th of this year.
Hi, I'm Amanda Bosch. I'm a planetary scientist and the Chief Operating Officer at Lowell Observatory. I study small bodies in the outer solar system, like Kuiper Belt objects and centaurs, as well as Pluto and Triton. There have been several events in the past that have really brought our focus to the importance of potential asteroid collisions with the Earth. One of them recently was the Chelyabinsk meteor explosion over the town of Chelyabinsk in Russia. While there weren't very many people injured in that particular event, it really does bring home the fact that small bodies can enter our atmosphere and even impact on the surface of the Earth. The Chelyabinsk meteor was thought to be about 20 meters in diameter, so it was not a very large one. But if there were something even larger that would come close to the Earth and even impact with the Earth, it could really affect the ability of life to continue on our planet. When we're looking for asteroids out in our solar system, the way to do that is to take some images of a portion of the sky. And you want these images, you want to have several images, usually 3 or more. And you want these images to be separated in time, so not taken right immediately after one another. And the reason for this is because we're looking for asteroids to move against the background stars. The background stars are so far away that they're basically at infinity, so they don't appear to move even as the Earth moves around the sun. However, things that are closer to us, like asteroids in the asteroid belt, or even bodies in the Kuiper Belt, which are much further away than the asteroid belt, those will appear to move against the background stars. So if we have a number of images of the same portion of the sky taken at different times, then what we can do is take those 2 or 3 or 5 images and compare them against each other. The background stars will not move, but anything that is within our solar system will appear to move, and you'll be able to track it. If you take several images at different times of the year, then you will be able to figure out, to calculate the orbit of that body around the sun. So this is a very old technique. In fact, it is the technique that Clyde Tombaugh used to discover Pluto back in 1930, just by watching solar system objects move against the background stars. And so there are a number of surveys underway that have in the past and are continuing to search for small bodies in our solar system. Sometimes they're discovered, accidentally, because people are observing something else and notice something moving in the images that they have taken. But that's the main approach for finding bodies in our solar system. So once we know that there is a small body out there with orbital parameters that will bring it close to the Earth, or maybe even impacting with the Earth, then what we need to do is to figure out ways to avoid that collision. First of all, the first step there is to figure out if there is going to be a collision. And while objects can be discovered that might be on a collision course, within just a short amount of time, like a month, it is more common that things are discovered that perhaps will collide with us on a longer time scale, like 10 years or 50 years or longer. If something like that were to be discovered, then what we would do is to study its orbit over the years to make sure, first of all, that it is going to collide with the Earth. The longer the baseline of data that you have, the better orbit you have. So you will be able to know more precisely if this object is going to be just passing near to the Earth or actually hitting the Earth. If the predictions based on these orbits say that it is actually going to be hitting the Earth, then what do we do? Then there's a number of studies underway to figure that out. And one of them, basically one of the things that you want to think about is, if we do know that something is going to collide with the Earth, say in 50 years, something like that, what we can do now is to change its orbit by just a tiny amount. And then over time, what that might mean is that a small change now would mean that it would miss the Earth later. And in fact, that's the approach that we want to take, because these are, even a 20-meter body is still huge, has a lot of mass, and will be difficult to deflect if we only had, a day's notice. So we really want to be able to know about these things earlier so that we can make a small change to its orbital parameters, so that it will, in 10 years or 50 years, will end up missing the Earth rather than hitting the Earth.
I am Brian Skiff. I'm a research associate at Lowell Observatory. I've been here for almost about 45 years, working in various capacities, mainly running telescopes and being a research assistant in various capacities at the observatory. I'm the guy who's been spending a huge number of nights, literally thousands of nights, running telescopes and taking pictures. In the old days, literally taking photographs on photographic plates, and in more recent years, using CCDs to do the same picture taking, and either to finding the new asteroids. I did probably 2/3 of the observing on the Lonio survey, where we were looking for the near-Earth asteroids. And then we had a substantial program of getting asteroid light curves, the rotational brightness variations as the asteroids tumbled in the sky, and they change brightness over a period of hours typically. and doing a lot of that observing, both for folks at Lowell and also colleagues elsewhere in the world. We've been doing various sorts of asteroid observing and research at the observatory almost since the beginning. Even during the very first Planet X search that Lowell started in 1905, there were photographs taken here on Mars Hill and shipped back on the train back to Lowell in Cambridge, Massachusetts, and he examined them and was very disappointed not to find Planet X, but he did find a number of new asteroids, ordinary asteroids, on those photographs. And things got a little more serious after the war, World War II, when work on the proper motion survey was being done using the Pluto camera, the 13-inch astrograph. And of course, a lot of photographs because they were covering a lot of sky, on a lot of those photographs, there were quite a large number of asteroids that were readily identified. And starting in about 1970, Ted Bohl became an astronomer here and started actual good research on the physical properties of asteroids, including discovering new ones, but also finding out about the colors and the chemical composition and so on. And that has continued with the latter-day asteroid maestro, Nick Moskovitz, who's doing a 21st century sort of asteroid research, looking at, again, at the composition and the origin of the bodies. In between those, at the end of Ted Bohl's career, he launched a program, a survey to hunt for near-Earth asteroids. And that was moderately successful. We found a couple of hundred new objects of that type. But we've really moved on from just the identification or the discovery of the asteroids to actually finding out the details about them. Well, there have been lots of fun experiences over the decades. In my case, maybe one of the feathers in our cap during the Lonio survey, which ran roughly from 1998 to 2010, was the rediscovery of an asteroid called Hermes, which was actually identified in the late 30s, but was because it was moving very fast across the sky and communications were poor and so on, it got lost. And there was some chance that it could be an Earth impactor. But on a particular night, I happened to find a really bright new, what I thought was a new asteroid. And of course, it was not known at the time because the uncertainty in the position of the object from 1937 was basically the entire sky, could have been anywhere in the sky. But as night proceeded around, I reported the data, and then as night proceeded around the Earth, additional observations were taken, and it was all identified within 12 hours, say, of being a rediscovery really, of Hermes, and is now known to be not a dangerous asteroid, but also known to be a binary. And so as all that transpired over the days following my rediscovery of that object, it was pretty exciting to follow all that.
My name is Bill Sheehan, and I am here as an astronomical historian to talk about Meteor Crater for Asteroid Day. I've been very interested in the history of the crater, not only from the standpoint of what it's told us about the science of impact and the importance of impacts on the surfaces of the moon and other planets, but also because it was one of the places the astronauts could access on the surface of the Earth that allowed them to get some idea of the moon. Basically, Meteor Crater is about 50,000 years old, and given the rapid erosion of any kind of geological features on the surface of the Earth, things on the Earth do not last very long. And so even though 50,000 years sounds like a long time to us, in our everyday lives, it's basically an instant of geologic time. And so on the whole Earth, even though there are many of these features that must have formed over the history of the Earth, it is the most pristine, well-preserved impact crater that's known. And so it gives us a really good laboratory to understand how these features formed and their significance on the early Earth and also on other celestial bodies. And that's why it was particularly interesting to the astronauts, because they were led into the crater by world-famous geologist Eugene Shoemaker, who was the first person really to figure out how these things form. And early on, craters on the moon, for instance, were thought maybe to be volcanic formations, because that's basically what geologists of that time were focused on. And people did admit that, yeah, occasionally a meteorite would hit the moon and form a crater, but they basically thought in terms of the mechanics of a bullet being fired into a target. Well, Gene Shoemaker and others realized that actually it's an explosive event. What you have is this object that is flying at high speed, so it has a lot of kinetic energy that suddenly encounters an immovable object, and it is all turned essentially into thermal energy, heat, and creates a huge blast, like an atomic bomb sort of thing. And this is what happened with Meteor Crater. Northern Arizona is a geological wonderland. Meteor Crater is unique as a feature that was formed by an asteroid impact. As I mentioned, it's the most well-preserved, pristine feature of its kind on the surface of the Earth. There are other similar features, but they're very much eroded and degraded and a lot harder to study. But in addition, this whole area, including that around Lowell Observatory, is the area where the San Francisco volcanic region exists. In other words, there are all sorts of cones from currently non-active volcanoes that dot the landscape. And so you not only are looking at Meteor Crater as the prototypical example of its kind, but also you have all of these volcanic cones that testify to another kind of geologic process. And then not far from here, of course, you have perhaps the most spectacular geological site in the world, certainly one of the most famous, the Grand Canyon, where you have erosion over time that essentially has excavated all of these stratigraphic layers that testify to the past history of the Earth. So it's just a fantastic area to understand the Earth as a living planet, a planet that has undergone all of these upheavals and changes and has left all of these interesting features for us to decipher.